All right, I want to mention a few things before I start the lecture. The first of which is that I just put up your online submission portal for your design project that is due this evening. I apologize for not getting that up earlier, and thank you to those who emailed me to remind me to do it. Another thing that I want to mention is that I have just uploaded homeworks 7 through 9. So homework 7 is on the material that we covered in our last class meeting. Homework 8 is on the material that we're going to cover in this class meeting. And homework 9 is on the material that we're going to cover next Wednesday. Monday, we are going to have a class, but I'm just going to use that class to work more example problems to get you guys more comfortable with this material. So there's not going to be anything new for Monday's lecture. I've also uploaded your exam for this material. The exam consists of 3 problems. One problem is a series RLC circuit like we're going to cover today. One problem is a parallel RLC circuit like we covered on Wednesday. And the third problem is a general RLC circuit like we're going to learn how to cover next Wednesday. So the material for this test is actually fairly brief. It's just the transient analysis of second order circuit. All right, so with that out of the way, let's talk about the transient analysis of series RLC circuits. So this is going to be extraordinarily similar to what we did in class on Wednesday. Let's consider a case where we have some voltage source Vs connected to a switch. This switch is going to open at t is equal to 0. And then we're going to have some resistor R here, some inductor L here, and some capacitor C over here, like so. Now I'm going to define some quantities for us. So the first thing that I'm going to define is a current I. And this current I will be flowing around this loop containing an R, L, and C, or a resistor, inductor, and capacitor once that switch opens up. So the current I is common to all of the elements, much like the voltage V was common to all of the elements in a parallel RLC circuit. Now I'm going to define the voltage drop across each of these components, and I'm going to do so with the current flowing into the positive polarity terminal, which means our capacitor voltage is going to be this. Our resistor voltage will be like so. And finally, our inductor voltage, excuse me, I totally wrote an I and I meant to put a V there, my apologies. So here is our inductor voltage. So we've got all of our polarities defined now. So during the transient condition, our circuit will look like this, where our voltage source is effectively disconnected from our RLC network. Here's VR, VL, VC, and I, and writing a Kirchhoff's voltage law equation around the right-hand path, we'll see that the voltage drop across our resistor plus the voltage drop across our inductor plus the voltage drop across our capacitor must be 0. I can express all three of these voltage drops in terms of my current I. So using Ohm's law, that's going to look like R times IR of T. For our inductor, we are going to have our derivative-based relationship here. So it's going to look like L, sorry, this shouldn't be IR, it should be I, DI by dt. And for our capacitor, we're going to need to use our integral-based relationship. So we'll have 1 over C times the integral from T naught to T of I of T prime dt prime plus VC at T naught is equal to 0. And once again, we have an integral differential equation. We're going to do the exact same thing that we did last time. We're simply going to take the derivative of both sides to get us to a second order differential equation. So when I take the derivative, and I'm going to rearrange things slightly here, I'm going to have L times the second derivative of I with respect to time plus R times the first derivative of I with respect to time plus 1 over C. Sorry, my stylus is acting up. There we go. Times the 0th derivative, or just the current function itself. And the derivative of the constant VC at T naught is equal to 0. So we have this second order differential equation, and much like I did in class on Wednesday, I'm going to simply divide everything through by a factor of L so that my coefficient for my second derivative term is 1. So that's going to give me d squared pi plus R over C, excuse me, R over L di by dt plus 1 over LC times I of t is equal to 0. And because it worked for us last time, we are going to guess that in this case, I of t will be of the form AE to the ST. Substituting that relationship in for I of t, we will have S squared AE to the ST plus S times R over L A to the ST plus 1 over LC times AE to the ST is equal to 0. And now I'm just going to factor things out. So we're going to have A times S squared plus S times R over L plus 1 over LC times E to the ST is equal to 0. And so once again, we have a second order polynomial as our characteristic equation. Since we have a second order characteristic equation, we will have two solutions. So I'm going to have S1 will be equal to negative R over L plus the square root of R over L squared minus 4 times 1 over LC. All divided by 2. Moving that 2 from our denominator up into the numerator, we get negative R over 2L plus the square root of R over 2L squared minus the square root of 1 over LC squared. And I can identify my Neper frequency for this system, alpha, as R over 2L. Once again, measured in Nepers per second. And my resonant frequency, omega naught, will once again be the square root of 1 over LC. So that I can express S1 now as negative alpha plus the square root of alpha squared minus omega naught squared. And S2 will be equal to negative alpha minus the square root of alpha squared minus omega naught squared. And from here, everything is literally identical to what we did on Wednesday, right? So the only difference between a series RLC circuit and a parallel RLC circuit is that they have different formulas to solve for alpha. Other than that, they behave in the exact same way. And so that's why I've laid out that table in that particular way. So just for the sake of argument, let me bring up that table again. So this would have been this meeting. First link, our table of parallel RLC responses. As we can see, all of the response equations and all of that kind of stuff, all of that is the same. The only thing that changes are how we find alpha for a parallel RLC circuit and how we find alpha for a series RLC circuit. Everything else is exactly the same. So I'm not going to continue along like we did on Wednesday because we've literally covered that material before. So instead, we're going to jump straight into working an example problem. All right, so this time our circuit of interest will be as follows. We're going to have a 3 amp source connected in parallel to a 4 ohm resistor. Here we're going to have a switch. And let's make our switch close at t is equal to 0. We are going to have a 1/4 of a Henry inductor here. Let's see, 40 millifarad capacitor here. And let's make this a 1 ohm resistor here. Let's define some things of interest. So this is going to be my current I. This will be the voltage drop across my inductor. This will be the voltage drop across my capacitor. And the quantity that we're interested in solving for this circuit will be the voltage drop across this resistor. And in order to solve for the voltage drop across this resistor, the easiest possible thing for us to do would be to say that it's going to be 1 ohms times this quantity I of t. So we're actually going to wind up solving for I of t and then using I of t to solve for VR of t. All right, so step 1, much like we did on Wednesday, we're going to analyze the circuit at t is equal to 0 minus. So at t is equal to 0 minus, our switch is open. So we have here our 3 amp source. Four ohm resistor. Our open circuit here representing our switch. A short circuit representing our inductor. An open circuit here representing our capacitor. And then our 1 ohm resistor. Here is our current I at 0 minus. Here is our voltage VC at 0 minus. Our voltage VL at 0 minus. And those are the 3 things that we're going to need to know what's going on with at t is equal to 0 minus. So should be very easy to see that I at 0 minus is 0 amps by inspection. VC at 0 minus is going to be 0 volts. And VL at 0 minus will also be 0 volts. So VL at 0 minus is 0 volts because we're taking the voltage drop over the short circuit representation of the inductor. So that one's fairly obvious. VC at 0 minus, that one's a little bit harder to see intuitively by looking at the circuit. That being said, we know that our current source is not connected to that RLC network to the right, so there's no reason there should be any voltage there. And if we played around with Kirchhoff's voltage law and things like that, we would find out that that would have to be the case as well. For step number 2, we are going to analyze our circuit at t is equal to 0 plus. So at t is equal to 0 plus, our switch is now closed. So we're going to have our 3 amp source here in parallel with our 4 ohm resistor. Our switch is closed. Our inductor is going to look like an open circuit because the inductor current cannot change abruptly, which means the inductor current has to still be 0. And then our capacitor is going to look like a short circuit because the capacitor voltage was 0, so it needs to stay 0 at t is equal to 0 plus. And then here we have our 1 ohm resistor. So let me label my quantities here. So here I have I at 0 minus, VL, excuse me, at 0 plus. This should be 0 plus as well. And then here is VC at 0 plus. I of 0 plus must be 0 amps because it was 0 amps at 0 minus. VC at 0 plus must be 0 volts because it was 0 volts at 0 minus. And what we are going to see now actually is that VL at 0 plus should be 12 volts. So let me explain specifically what I mean by that. I'm going to use colors here so we can denote some things, right? So this is the node connected to the negative polarity terminal of my inductor, okay? Because there's no current flowing through the 1 ohm resistor, this 1 ohm resistor does not have a voltage drop over it, so we're still at the same node when we come down here, and it wraps around like so. So the negative polarity terminal of the inductor is at the same potential as the bottom terminal of the 4 ohm resistor. Well, the positive polarity terminal of the inductor is at the same node as the top node of the 4 ohm resistor, which means for all intents and purposes here, our inductor is behaving as if it were in parallel with that 4 ohm resistor. Since it's in parallel with the 4 ohm resistor, it must have the same voltage drop as the 4 ohm resistor, and simple application of Ohm's law tells us that 3 amps times 4 ohms is equal to 12 volts. So our inductor voltage has shifted from 0 volts at t is equal to 0 minus to 12 volts at t is equal to 0 plus. For step number, sorry, let me make that line not as thick. For step number 3, we're going to analyze the circuit at t is equal to infinity. So at t is equal to infinity, our switch is still closed. We have our 3 amp source in parallel with our 4 ohm resistor. Here is our closed switch. Here is our inductor, which looks like a short circuit because we're at DC steady state. My capacitor is going to look like an open circuit because we're at DC steady state. Here is my 1 ohm resistor. So this is VL at infinity. This is VC at infinity. And this is I at infinity. So by inspection, I at infinity is 0 amps. And VL at infinity is 0 volts. VC at infinity should be 12 volts for the exact same reason that VL at 0 plus was 12 volts. So I'm not going to re-explain that. We should all be okay there. So we have all of our parts, or the values for all of our parts, at t is equal to 0 minus, t is equal to 0 plus, and t is equal to infinity. Now we need to go to step 4, which is to calculate alpha and omega naught and determine the type of response that our circuit will have. So this is going to be a little bit more involved than what we did on Wednesday because this problem was a little bit more difficult, okay? So what I mean by that specifically is we have multiple resistors and we need to figure out what the relationship between those resistors is, if any, in order to determine our equivalent resistance, which we're going to use to calculate alpha, okay? So effectively what we are going to be doing here to calculate our equivalent resistance is we are going to find the resistance or the Thevenin resistance seen by our energy storage elements during the transient condition. Okay, so I'm going to draw our circuit during the transient condition. Here we have a 3 amp source in parallel with a 4 ohm resistor. I'm going to simplify some things here. I'm not going to show the switch because it's closed, so it just looks like a short circuit. So here's our inductor. I'm just going to call it L, partially because I don't remember what value I gave it. Here's my capacitor, just going to call it C for now. Here's my 1 ohm resistor. Okay. So we're finding the Thevenin equivalent resistance as seen by our energy storage elements, which in this case is an inductor and a capacitor in series. So I'm going to take that inductor and capacitor out, leaving behind an open circuited set of terminals. And looking into these terminals is how I'm going to find REQ. When I'm finding the equivalent resistance of a network directly, I need to make sure that I'm looking at a dead network, meaning that my current source here needs to be turned off, and an off current source looks like an open circuit. So from this, I can see that REQ is simply 1 ohms plus 4 ohms is 5 ohms. From this, alpha is R over 2L. So that's 5 ohms over 2 times, if I'm not mistaken, 1/4 of a Henry. Let me scroll up here. Yep. So 5 over a half should be 10 neppers per second. If my mental math is correct, I'm going to just verify that on my calculator really quickly because I don't want to mess things up. So 5 over 2 times 0.25 is indeed 10. Omega naught is going to be the square root of 1 over 1/4 of a Henry times 40 millifarads. I'm worried this is also going to be 10. If it is, we'll just change one of our values here. Let's see. Square root of 1 over 1/4 times 0.04. Yep, that is also 10. The reason why I don't want this to also be 10 is so I can show you an example of a different type of response, right? There's nothing wrong with it being 10 here, but effectively we're going to be doing almost the exact same thing that we did on Wednesday, and I want to show you a different type. So all I'm going to do is I'm going to change the value of this capacitor to 50 millifarads, and that should be enough to fix things. So let me go up here and correct that. So let me redo this. All right, so when I put this as 50 millifarads, I get 8.944 and some change. This is going to be in radians per second. And just for the sake of argument, I'm going to store this in my calculator as, I think, D for right now. So we can see that alpha is greater than omega naught, which means that this is an overdamped response. And since I'm dealing with an overdamped response, I'm going to need to know what S1 and S2 are. So S1 is negative alpha plus the square root of alpha squared minus omega naught squared. So I'm going to put that in my calculator really quickly. Negative 10 plus the square root of 10 squared minus what I have in my calculator as d squared. Which I get to be negative 5.528 and some change. This has units of per second. I'm going to store this in my calculator as A. And S2 is negative alpha, minus alpha squared minus omega naught squared. So I'm going to go ahead and throw that into my calculator. I get negative 14.472 per second and some change. And I'm going to store this as B. All right, so our last step in solving for that resistor current that we're interested in is to solve for our response equation. And so this is going to be very similar to what we did on Wednesday, but because we have an overdamped response, we're going to use a different part of the table, okay? So I had mentioned briefly earlier, and I'll scroll up here and show it to you, that we are relying on our ability to calculate our current I of t in order to determine our voltage VR of t, okay? So I of t is the same thing as my inductor current. So that's going to be my first relationship, right? So I'm going to have I of t is equal to A1 e to the S1t plus A2 e to the S2t plus I at infinity. And I at 0 plus then becomes A1 plus A2 plus I at infinity. So I at 0 plus was 0, if I'm not mistaken. And I at infinity was also 0. So what I'm going to get from this is A1 plus A2 is equal to 0. All right. This is my first relationship that I'm going to use to solve for my coefficients. Now I'm going to use the inductor voltage relationship because that's the derivative-based relationship with the inductor current. So I can say that VL of t is L di by dt. And if we look at our table, that's just going to be L times S1 A1 e to the S1t plus S2 A2 e to the S2t at t is equal to 0 plus. This reduces to L times S1 A1 plus S2 A2. So L times S1, actually, let's see. So VL at 0 plus was 12 volts. Yes. So this is going to be 12 volts is equal to L 1/4 times S1, which I had stored in my calculator as A, negative 1.382 A1. And now I'm going to have L times S2. So that's 1/4 times what I had stored in my calculator as B. Negative 3.618. And some change. This is, A2. And this is my second relationship. And so now I'm just going to solve this system, okay, which is part of the reason why I stored things in my calculator. So going to my system solver, I have a 2x2 system. The coefficient for A1 in my first equation is +1. The coefficient for A2 in my first equation is +1, and my constant term is 0. In my second equation, my coefficient for A1 is negative 1.382. My coefficient for A2 in my second equation is negative 3.618. And my constant term is 12. Solving this system of equations, I find that A1 is equal to 5.366 and some change amps. And A2 is negative 5.366 and some change amps. From this, I can say that I of t is going to be 5.366 e to the negative, or excuse me, e to the s1t. So s1 was negative 5.528 minus 5.366 e to the s2, where s2 was negative 14.472 t, and I at infinity was 0, so that's just going to be amps here. VR is just 1 ohm times I of t. So that's going to be literally the exact same equation, except that we're going to change the units from amps to volts. So 366 e to the minus 5.528 t minus 5.366 e to the negative 14.472 t volts. All right, so what we're going to do now is we are going to simulate this circuit in LT Spice and verify that we have done all of our analysis correctly. So here's LT Spice. I'm going to open up a new schematic diagram. Let's see. So during my transit condition, I have a current source. It is pointed up. And it has a value of 3 amps. I have a 4 ohm resistor that'll go right here. My switch is going to look like a short circuit, so I'm just going to put my inductor here. So 1/4 is the same as 0.25. Let's see. My capacitor is going to go here. We made this 50 millifarads so that it wouldn't be a critically damped circuit again. apply this over here, and then put my 1 ohm resistor over here. I mentioned earlier, or at least I mentioned in class on Wednesday, that I usually put the ground at the negative polarity terminal of my capacitor because it makes it very easy for me to set my initial conditions. I'm going to go ahead and label the positive polarity node of my capacitor as VC here. I think that's all I need to do. Oh, I need to put my initial conditions in, right? So the initial condition on my capacitor voltage was 0 volts. The initial condition on my inductor current was 0 amps. And let's see. Let's run this for, I'm just going to guesstimate here, 3 seconds. We might need to go back and change this. So I'm trying to find the voltage drop across my resistor with positive polarity on top. So because this node is grounded, what node is this? Negative, node 2. So the voltage drop across my resistor is going to be negative the voltage at node 2. So I'm just going to add a trace. It says negative the voltage at node 2. This is what I get. And now I'm going to type in my mathematical expression. So let me refresh myself, 5.366 times the exponential of negative 5.528, if I can read my handwriting, times time minus 5.366 times the exponential of negative, excuse me, 14.472 times time and my blue curve completely overlaps my green curve, and the scale on the left-hand side of the screen matches the scale on the right-hand side of the screen. So all of my analysis was done correctly.